Hello everyone. In today's lecture, we are going to discuss about the introduction to counters in the context of digital electronics. So in digital logic circuits, if we see counters plays a major role. There are two types of digital logic circuits in general. One is combinational logic circuits and the other one is sequential logic circuits. So if we see the combinational logic circuits, any circuit which do not have a memory, or if a digital circuit do not have a feedback path, then we call it as a combinational logic circuit. For example, adders, subtractors, multiplexers, encoders, all these are combinational logic circuits. It do not have any feedback. It don't have any memory. The present output depends only on the present input. On the other case, if we consider a sequential logic circuit, it has memory. It has a feedback system. And different types of sequential logic circuits are there. And the most commonly used are registers, shift registers and counters. In today's lecture, we are going to discuss about counters and its types. Counters are sequential logic circuits. Flip-flops are essential components in clocked sequential circuits. So we know what is sequential circuits now. Counters are sequential, that is counters, they have feedback path, they has a memory system. And the basic building blocks of flip-flops. Two common sequential circuits are counters and registers. Counters is frequently used in digital computers and digital systems to record the number of events occurring in specific time interval. There are different applications of counters. We in practical, in real time, we know in n number of places we use counters. Here few are listed here: frequency counters, digital clock for time measurement, in odometers, analog to digital converters, frequency dividers, and in program counters, that is a clock. In a system, everything is based on clock. Program counter increases one by one based on counters. Types of counters. There are two types of counters. One is asynchronous counters, which is also known as ripple counter, and the other one is synchronous counters. So if we see an asynchronous counter, uh, in an asynchronous counter, see if you see here, here two flip-flops, which is the basic building block of a counter. So two flip-flops are being used. First flip-flop, see once we use flip-flops, then obviously it works based on clock. So here the clock is being given to the first flip-flop only. And second flip-flop also need a clock, but a general clock was not being given. See how the clock is being given? The output of the first flip-flop is given as a clock to the second flip-flop. So this is the main difference between an asynchronous counter and synchronous counters. Later we look into synchronous counters. So only the first flip-flop is driven by the main clock, and the remaining all flip-flops receives the output of the previous flip-flop as clock. This is asynchronous counter. That is, parallelly we do not give main clock to all the flip-flops simultaneously. Now you see how it works. Now this is a enlarged diagram, detailed diagram. Here we use four flip-flops, and here this is the clock which is being given to the first flip-flop. The second flip-flop receives the clock from the output of the first flip-flop. Then the third receives the clock from the output of the second flip-flop. And fourth, output of the third flip-flop. Right? So this is a JK flip-flop, and so we have given high. And now you see here, this is a timing diagram for an asynchronous counter. Initially for the first flip-flop, we give a normal clock, right? And if you see the second, that is this Q0, this is a Q0, right? here this bubble with an arrow, the arrow shows that the clocks are edge triggered clocks, and the bubble with an arrow, it shows that it is negative edge triggered clock. So see, when there is a negative edge, that is when there is a transition from 1 to 0 in a clock, we call that as a negative edge triggered clock. So during the negative edge or the trailing edge, see, the tasks will be initiated. So Q naught has been produced in every negative edges. And you see here Q1, that is this output, is generated in the negative edge of this Q naught, not from the clock. If you see the dashed lines is being given here, the first Q naught is based on this negative edge, but this Q1 is based on the Q naught. Output of Q1 depends on the Q naught, right? And output of Q2, see, it starts in this negative edge, that is the negative edge of Q1, which is the previous output, and similarly Q3 based on Q2. So this is how, so if you see here, you can see the difference. This dotted line shows the initiation of the task. So here the frequency is being divided in an asynchronous counter. If you see the output waveforms, the frequency is being divided. This is asynchronous counter. Coming to synchronous counter, it has one global clock. This is again the simplest diagram. See a clock, this is the main clock, which is given simultaneously to this flip-flop as well as this flip-flop. So this is synchronous counters. It is also known as parallel counters since the clock is being given to all the flip-flops parallelly or simultaneously. And in synchronous also we have leading edge or trailing edge, right? Both positive edge or negative edge triggered clocks can be used. This is synchronous counters timing diagram. If you see here, this is the clock, and see here the initiation takes place. Again, this is a negative edge triggered clock. So in the negative edge, the action has been initiated. In every negative edges, the action has been initiated. It do not wait for the output of the previous state. So this is all about the introduction to counters. And this is for your assessment. And thank you.